Okay, good afternoon, everybody. Welcome to the final session. So we're between you and beer, I think. And so we're going to change gear a bit, and we're going to be talking more about early disease, early detection and prevention in this session. I'm Doug Easton. I'm from the University of Cambridge. That's not Cambridge, just in case you're wondering. So I'm going to talk specifically about cancer risk prediction, and I'm going to focus on breast cancer, which is what I mainly work on. The issues are more or less the same for the other common cancers, particularly colorectal and prostate cancer. I have no conflicts of interest, unfortunately. One of the reasons I'm primarily going to concentrate on genetic risk prediction, but there are other ways that one can predict cancer risk, and they're all important. For breast cancer, there are three main components to this. There's genetics, there's imaging, breast imaging, and there's known lifestyle and reproductive risk factors, and they're all important. How you combine them together is one of the key questions. There's emerging evidence that other omics might be useful for risk prediction, but that's much more uncertain at the moment. And one of the interesting things about using genetics for risk prediction and understanding the genetic basis of the disease is both helpful for risk prediction and early detection potentially, but it's also interesting in the terms of understanding mechanisms and how it relates to tumor genomics. So this is always the most important slide. So if you go to sleep after this one, that's okay. So this is essentially everything today we know about breast cancer genetics on one slide. And so you can summarize what we know about genetics on a graph like this, where the x-axis is frequency and the y-axis is risk. And there are sort of three main categories, really. Up here are the two genes that most of you will have heard of, I hope, BRCA1 and BRCA2. They're the most important clinically, been known about for 20 years. And then there are these two other categories. There are risk SNPs. These are common variants in the population, each of which confer a relatively small risk of the disease, but there's a huge number of them. And then there's this rather more nebulous category of other genes which confer various risks, most of which are not very well defined. And there's a lot of interest in this area. I'm going to concentrate mainly on the SNPs to begin with, and I'll come back to this point towards the end of my talk. So we've heard a lot about fascinating technologies over the course of the day. So most of this is sort of a bit more basic in terms of technology. We only really have two technologies that we use for most of this work, one of which is large-scale array genotyping, and that's been the most important in terms of SNP discovery, and the other one is large-scale sequencing, which is becoming more important for the other genes. And most of the data that we have has come through two very large experiments, one of which, the ICOGS experiment, has been published. The other one is the Oncoarray, which is finished but not yet published, but say something about that. And the point here is that array genotyping is relatively cheap, so you can do it on very large numbers. And so these arrays have been genotyped in literally hundreds of thousands of individuals, probably up to about 1 million if you count all the cancers together. And that's possible because there are many large-scale epidemiological studies throughout the world, and so we've been able to put this data together. And it's necessary to do the studies on this scale because the effect of individual variants is quite small, so you can only really establish them if you do very large studies. And this is mainly a collaboration between a number of groups funded by a number of funders, both here in the UK and abroad. So this is what you get out of the array genotyping. So these are what's called Manhattan plots, so each little circle here is a SNP. This is the genome. These are p-values, and these spikes here are regions of the genome which are associated with risk. On the left-hand side is everything we know. This is putting together the data from both the ICOGS and the Oncoarray experiments. And there are some regions which have been known for a long time, like FGFR2, TOX3, and so forth. Once you get rid of the ones you knew about already, what's been discovered over the last year through the Oncoarray is a huge number of additional loci. So we're now up to about 170 regions of the genome with common variants associated with breast cancer risk. Most of which, of course, we know nothing about the underlying biology, but in few cases we do. One of the main themes which emerges is that there's a clear subtyping effect. Maybe not surprised to learn that. And in particular, there's a clear distinction between ER-positive and ER-negative disease. So most SNPs associated with breast cancer are actually associated with ER-positive breast cancer, including some of the more important ones, like the ones near FGFR2 and CCND1. A smaller subset are associated with ER-negative disease. And then there's a third subtype which appear to be associated more or less equally with both subtypes. So there's some overlap in the genetics of ER-positive and ER-negative breast cancer, but they're also distinct components. One of the things which has been gradually become clearer is that, as I say, we don't know in most cases what the underlying biology is, but we do know that most of, although not all, but most of the variants are non-coding variants located in regulatory sequences. So if you look across all the variants that are associated with risk, there's an enrichment for conserved regions, for enhancer regions, and particularly for transcription factor binding sites. And the clearest evidence is for FOXA1 binding sites. Again, that might not surprise you, which is they're about fourfold enriched, and that appears to be, not surprisingly, particularly for the loci associated with ER-positive breast cancer. And if you drill down to particular regions, you can start to work out what's going on in more detail. So just show one example. So this is a region which has recently been published. Happens to be on 6q25 around the estrogen receptor gene, rather obvious target. And what you find is that, in fact, although it was originally identified as one signal, in fact it's several signals. So there's at least 5, and I think from the latest data, maybe as many as 9 independent signals. As expected, none of them are in the gene itself. Most of them are either upstream or downstream of the gene in enhancer regions, which you can show using 3C experiments, interact with the promoter of ESR1, and also another gene up here, which I think isn't shown here. But anyway, it's the predominant interaction with ESR1. So that's an example where we do appear to have a clear candidate gene, which is presumably the target of the association. There are a lot of pathways involved here. So if you look at the genes to the extent that we can identify them that are involved, a whole series of different pathways are involved. The most predominant one is FGF signaling, but there's a number of other interesting targets, some of which have never previously been suggested, and so there's a lot of biology to try and work out there. How does one actually use this information in practice, though? I mean, the point is that the individual variants are not very predictive, so nobody's going to have a test for FGFR2 variants. If you're going to have a test for risk prediction, it's got to be on the basis of all the variants combined. And that's much more predictive because there are such a large number of them. That's illustrated here. So these blue bars, this is the distribution of the number of risk alleles that people in the population carry. So at this stage, based on 77 risk variants, on average, women in the population carry about 70 risk variants, but some carry a lot more and some carry a lot less. You get this nice normal distribution of risk variants. And because these risk variants are risk variants, breast cancer cases, on average, have a higher number of variants. And so you've got a distribution which is shifted to the right. And the extent to which it's shifted to the right is a measure of how predictive these SNPs are in terms of risk prediction. And so you can do that, put that together mathematically by essentially adding the effects of the variants together to form what's called a polygenic risk score. And we've tested that on both the ICOGS and the Oncoarray data sets. And you do indeed get quite a nice risk prediction. So this is looking now at absolute risk of breast cancer according to where you lie on this distribution. So on the left here, this is all breast cancer. So the average risk is about 9%, or 10%. But you can see that the women in the top 20% of the distribution have a much higher risk, getting on for 18%. Women in the bottom 20% have a much lower risk. So you're getting up to information which could be useful in terms of considering screening strategies or chemoprevention, for example. On the right here, this is for ER-positive disease. Because there are more SNPs for ER-positive disease, the prediction is better. It's also somewhat predictive for ER-negative disease, but not yet as good. An important point is that this isn't just the same as family history. Family history of breast cancer is also a very predictive factor, but the SNP prediction works in women who do or don't have a family history. In fact, it's more important in women with a family history because the effects essentially multiply up. So it's in terms of absolute risk prediction, SNP profiling is more useful in women with a family history. So alongside using the SNP prediction, there's also been recently a lot of interest in trying to understand these other genes that are involved in germline susceptibility to breast cancer. Some of them have been known about for some time, some of them are newer. And one of the reasons it's become kind of clinically important is that gene panel testing has become widely available, particularly in the US. A number of companies have sprung up offering such tests. And these gene panels vary a lot. So there's not very much consistency actually between what different companies offer. One of the challenges here is that the data for these other genes is actually rather poor. Many of the genes which are on panels, the evidence that they're associated with risk is actually rather limited. And one of the main challenges at the moment is to try and extend the idea of the SNP panel, SNP testing, to these other genes and applying this on very large scale so we can actually get some decent risk estimates. We reviewed the evidence last year and we defined these 11 genes where we thought that the evidence for being involved in breast cancer susceptibility was reliable. BRCA1 and 2, obviously no surprise, and these are the other ones. The most important one probably is PALB2, which confers a risk which is a bit less than BRCA1 and 2, but more than the other genes. And that's one which I know beginning to be introduced into clinical guidelines in a number of countries now. But it's important to remember that these risks are highly variable. How you would counsel somebody who has a BRCA1 and 2 mutation is quite different from somebody who's a carrier of some of these other variants. And one of the challenges is that the risks depend not only on the gene, but also on the variant. So this is a classic example, which is the CHEK2 gene, one of the other DNA repair genes. We know that truncating variants in CHEK2 confer a risk of about 2-fold for breast cancer. And that's quite reliably known through studies of this variant 1100 del C. But missense variants in this gene also confer a risk, but it's not the same risk. So that's a major challenge in terms of putting together studies that will get reliable risk estimates for all these variants, most of which are very rare. Now, I mentioned that there's an important imaging component here, and so the other major risk factor that we know about for breast cancer is breast density, which you can study in various ways, but predominantly on mammograms. And essentially, breast density is roughly as predictive as SNPs. So if you estimate what the odds ratio is per unit change in breast density, it's about the same as it is for the SNPs, and these two factors are more or less independent. So one of the aims is to really put this all together and define what's the risk based on combinations of the SNPs, the genes, the other risk factors, and the breast density. And you can sort of illustrate that. This is an ROC curve illustrating the idea. So this red line, this is the ROC curve that you get with the current genetic loci. It's better than the other risk factors. It's a bit better than breast density. But the real gain is putting them all together. And then you can get up to quite reasonable predictions with an area under the curve a bit better than 0.7. Or put another way, if you put these together again, here this is the blue line is now the distribution of all risk factors in the population, and the red line is for cases. So if you take slightly arbitrarily define women at more than 3-fold risk as being at high risk, that's roughly what the NICE guidelines say. You can identify about 4% of the population at high risk, and they account for about 18% of all breast cancer. At the other end, so these are women who might be eligible for MRI screening or chemo prevention. At the other end of the scale, you can identify about 20% of the population who have a risk less than a third of the general population risk, and they account for only about 4% of breast cancer. And you could argue that these women, and has been argued, shouldn't really be screened at all. And just by way of comparison, BRCA1 and 2 mutations account for only about 0.4% of the population. So putting this all together, you can essentially increase the number of women who are defined at high risk by about 10-fold. So just a few words about how we might do better. So a number of ways in which we could improve this. Incorporating more SNPs is one, and both by getting denser mapping, as I illustrated for ESR1, and incorporating genomic and functional information to define the risk SNPs better. For the rare variants, the main issue is larger sequencing studies and better ways of classifying variants so we can identify the variants which are at-risk variants. There are a number of ways in which the imaging studies could be improved. The number of studies trying to use automated measures of density. There are other measures that you can use, for example, parenchymal enhancement on MRI, and there's a certain amount of evidence suggesting that other measures that measure texture rather than just density may also be predictive of risk. And then there's a more open question about whether other phenotypes that you can measure in blood, so microRNAs, methylation markers and so forth, are also predictive of risk. There's some suggestion. The study's a bit inconclusive at the moment. Just in terms of the SNPs and the genetics, we reckon we've probably explained maybe about 60% of all the genetic susceptibility, if you define that by the familial risk of breast cancer. So there's about another 40% still to explain, and that's presumably some combination of common and rare variants. How much of that we can get at is still an open question. But there's certainly potential for improving the risk prediction if we could define those SNPs better. So, just to conclude, I hope I've shown you that breast cancer risk can be usefully stratified, and it should improve the cost effectiveness of screening and prevention strategies. The most important factors to consider are SNPs combined into a polygenic risk score and breast density. The PRS can be improved by incorporating additional genomic data. I think the value of gene panel testing is a bit more of an open question. For some of the genes it's valuable, for some not. But combining all the risk factors together can be much more informative. One of the key questions, however, is going to be how acceptable stratified prevention will be in practice, and that's a much more tricky question involving behavioral science and health economics and the politicians. So I'll stop there. Many, many people to thank. The people on the left are mainly the people from Cambridge, many of the other collaborators, and particularly the Breast Cancer Association consultants, a collaboration of about 100 different groups without whom none of this would have been possible, and of course the funders. So thank you, and I'll stop there. Time for a couple of questions, I think, if there are any.
Yeah,
yes.
Yeah, I just want to know. So it seems that with your combined predictive factor, you can really identify the patient with very low risk of breast cancer. So what is the gap between your data and the clinical implementation? Because, I mean, I don't understand, because these data are very robust, so I don't understand why we are still doing mammogram to this patient. I mean, we should be able to implement this quite quickly.
So I don't think that's not a scientific issue. That's more of a, if you like, a political issue. I mean, it's very, we've had a lot of discussions about that. And it would be, from a sort of health economic perspective, it would make much more sense to take those women out of screening or just give them much more limited screening. You probably would be, that would be a good strategy, but politically that's much more difficult to implement, unfortunately. Charlie.
Doug, very nice talk, thank you. The 40% sort of the black box, which we don't know yet in terms of unexplained risk, is it totally beyond the realms of possibility that mosaicism may contribute to some of the risk, where you're seeing particular, let's say, deleterious SNPs, in mammary tissue that you're not sampling by just sort of standard germline analyses?
That's certainly possible. That contributes to the risk. It wouldn't contribute to the 40% though, because that 40% is by definition what's hereditary. So if that's, unless some component of that was also hereditary, so that would be like an additional thing. Okay.
I was very surprised to see that you show that there are many more SNPs for ER positive as compared to ER negative breast cancer. Do you have any scientific explanation on that differences?
Yeah, so that's a good question. So I think the difference in the numbers is mainly power. So it's mainly just that the ER negative sample size is much smaller. And a lot of the studies are much better now. Most of the studies have really good data on the subtyping, so that seems to be the main. I think if you had infinite knowledge, infinite samples, it'd probably be about the same.
According to the curve you showed about the high-risk patients, what do you think about stopping to do mammograms for these patients and do IRM, nuclear medicine, whatever, but without X-ray?
So using MRI, yeah, well, I think that would be the logical outcome. You know, that obviously has significant cost implications. So I mean, I think that would take a while to actually implement. Yeah, exactly. But yeah, I think that would be the logic, because their risk is comparable to that for BRCA1 and 2 mutations, for which in most countries the guidelines are for MRI screening. So yeah. Okay, thank you very much.